your usual data science workflow can get more than 100 times faster without changing a single line of code. Indeed, thanks to GPUs, Pandas can run as fast as the NVIDIA stock is climbing. And in this video, I will show you how it works with a concrete example and how you can use it to your advantage. Let's go. Python is the master of illusions. It is slow, way slower than other compiled languages, but it shows similar performance in some contexts. How is that possible? Well, Python is an interpreted language, meaning that it has a runtime that executes the Python scripts without first compiling it to language code. It gives you a lot of flexibility, but you pay the performance price. However, Python is just an orchestrator in many cases, invoking libraries written in fast compiled languages like C. Thus, it inherits their performance while providing an easier interface thanks to its simplicity. For instance, Pandas, which is one of the most popular libraries to handle data in Python, is using NumPy in the backend, which is written in C and is super fast, providing you great performance to analyze data. Now, what is faster than CPU code? GPU kernels, at least in some cases. RapidAI is maintaining cuDF, a Python GPU DataFrame library built on top of the Apache Arrow memory format and implementing an API similar to Pandas. And the result is more than 100 times faster execution on DataFrame operation, depending on the GPU and the kind of operation you are executing. Now let's see a concrete example. I've built a Google Colab notebook connected to a T4 GPU, which is one of the less powerful available on Colab, but still useful to compare the GPU and CPU runtime. The first thing is to set your credentials because we are going to use Kaggle to download a dataset. You can use the secrets on the Google Colab notebook and set the Kaggle key and the Kaggle username. The first thing is to install the Kaggle library that will allow us to download the dataset. To do so, we set the environment variable using the secret we just set before. Then we download the dataset. It's a dataset about YouTube statistics, so you have tags, publish time, video IDs, and so on, country of publication. Then we have some imports. We import Pandas as PDCPU and cuDF as PDGPU. It's important because we want to distinguish between Pandas running on the CPU and on the GPU, and we will do the benchmark. The next step is to create a load function that will load our data based on the mode being CPU or GPU that will control whether we use Pandas CPU or Pandas GPU. To do so, we just create an array of data frames, we load all the data ending with CSV, and we append it to the array and return the concatenated data frame. The output of this function will be either a CPU data frame or GPU data frame, thus conditioning how the operation will execute will run. If we have the CPU data frame, it will run on the CPU. If we have the GPU data frames, subsequent operation will run on the GPU. Now it's time to define our benchmark functions. We have three of them: the explode benchmark, title length benchmark, and pivot benchmark. Let's see how they work in detail. First, the exploding benchmark. This one takes as input a simplified version of the data frame containing only the index and the tags column. Tags are strings separated by a separator. The first step is to split by the separator to get a list. Then we explode the tags column to get a row per tag. So we keep here the same index, but we have one row for each element in the tags list. The last step is to count, so we get a count for each tag. So here 2 for the tag 1, 2 for tag 2, and only 1 for the tag 3. The second one is the title length benchmark. Very simple. This one takes as input a simplified data frame, taking only the index and the title column. Then we just compute the length of each string in the title column, and we get the average. So here it would be 7, 8, 9, and 8 as the mean. And the last one is the pivot benchmark. We take as input a data frame containing the columns video ID, exploded tags, year of publication, and views. Then, for the pivot, we use for the index the exploded tags, as the columns the year, and for the values the average views. So for tag 1 we get 100 views in 2019 and 0 in 2020. For task 2, we get 0 views in 2019, but we get an average of 750 views on year 2020. Now let's move on running the benchmark. To make our life easier, we create a class named the runner to execute our benchmark. It takes as input a function and the number of time to execute it, and provides utility to get the average running time and the return value. We create a CPU and a GPU runner. The first thing is to benchmark the data loading. By moving from CPU to GPU, we already get a 10x speedup just for loading the data. Then for exploding, we are 21 times faster. For computing the average data length, we are 55 times faster, and for pivoting, also around 20 times faster. Not bad using the slowest GPU available on Colab, and without changing a single line of code in our Pandas execution. Now I want to quickly show you some utilities. You do not have to import cuDF. You can just import Pandas and use the magic function from the notebook to load cuDF Pandas. It will replace the Pandas implementation with the GPU one. The next thing is to use the line profiler from cuDF. It helps you benchmark your code and see how much time you are spending on the GPU and CPU. So after running this cell, you would get an array with line by line the GPU time and CPU time spent for each line. I have to mention that there are a few limitations because of the GPU runtime. For instance, there are limits on the number of strings you can load, the maximum number of rows or columns, and some of the Pandas APIs are not implemented yet. I encountered those problems a few times, but for most workflow, you won't have issues and you will enjoy the huge performance boost. Today we saw that Pandas on GPU is dope and will speed up your data science work significantly. It works thanks to cuDF seamlessly running your high-level Python code on GPU. So next time you hear Python is slow, prove them wrong by unleashing your GPU power with cuDF. See you in the next one.